You should see the screen, the full screen?
Yes, not in full screen mode. I think we are looking at the...
Now it's full screen, right?
Somehow it's totally black.
I used...
I think that's okay. This one's okay, readable. We are seeing the tab also, so I assume that that's not what you intended, but
is this one okay?
Yeah, this one is a full screen mode, your presentation.
Okay, thank you. So today I will talk about message passing algorithms of graphical models. I have joined iTHEMS since last April. So already 4 months has passed. I'm not very new anymore. And I have given, first I will introduce myself briefly. I'm a special postdoc researcher of basic science. This is my second year. Last year I was in AIP in mathematical, statistical and mathematical science group. Before that, I did a postdoc with Professor Yoshiyuki Kabashima and also another postdoc in Finland, Aalto University. I gave a talk in biology seminar about this period of work. I applied statistical mechanics to genome-wide epistasis analysis. My education background is I did all my university education in Tokyo Institute of Technology. First, I joined the physics department, and my thesis was supervised by Nishimori, Hidetoshi, Professor Nishimori. Then I went to Kabashima Yoshiyuki lab. My main focus was on statistical mechanics physics applied to 1-bit compressed sensing. So it's already a boundary area between physics and signal processing. We invited Professor Kabashima Yoshiyuki to give us a lecture on replica method recently. Today, I'm going to talk about another part of my PhD studies, the belief propagation algorithm. Another name is message passing algorithm. So first, I have to introduce the factor graph. The factor graph is a bipartite graph representing the factorization of a function. In probability theory, the factor graphs are used to represent factorization of a probability distribution function, enabling efficient computations, such as computation of marginal distributions through the sum product algorithm. The successful application are error correcting codes, such as low density parity check codes and turbo codes. And usually the marginal inference problem is NP hard, but using factor graph, and when the graph has a special structure, the complexity can be dramatically reduced. Here's a simple example of the graph. For example, function g over n variables can be factorized to m part functions f, and each f function is represented by the black box in the graph, and the circles are the variable nodes. And here is a loop. When there's a loop in the graph, the computation of the marginal is more difficult. And the graph often represented in this form: variable vertices, and factor vertices, and edges. Here's an example of the Edward Anderson model expressed in factor graph. This is a classical model in statistical mechanics used to modeling spin glasses. The energy function contains 2 parts. One part is the correlating part, another part is the external field. independently on each variables. The Boltzmann distribution is written as a probability distribution factorized to many parts. And this correlating part represented by the black box on the graph, and the gray box is representing the external field, and all the neighbors are connected on this model. Another example is Hamming code. When there's a uniform probability distribution over the code words, this is the distribution of the code words. This is an example of 7 variable nodes. So there's 3 parity check conditions represented by the 3 black dots on the graph. Another example is satisfiability problem. This is a decision-making problem. Also can be received. Many conditions contains the logical and can be represented on the graph. So the message passing on the vector graph is, we have 2 kinds of messages, from variable nodes to function nodes, and the function nodes to variable nodes. So for example, messages from previous step, the updating rules from previous step to the next step is of the message from J to A is a product of all the messages coming to J, is excluded these edges. And these are all represented by previous messages. And another way is message from A to J is represented by all the message coming to A is here, removed by remove the part of the J, and also summation over the A variable, not taking the value of J on the function phi. So it looks very complicated. We will, in the algorithm, we will iteratively doing this message passing again and again. This is the standard routine of the message passing algorithm, often also called belief propagation algorithms. Other names are AMP, BP, or cavity method. It's related to statistical physics, encoding theory, artificial intelligence, and applied to many, many problems. So the standard routine is set an initial condition for the random variables, and we set the maximum routine number. For each JA pair on the graph, we compute message A to J, and we compute message J to A. Then we compute the updating errors, the maximum message change. If the message change is smaller than some threshold we set it, then the algorithm is converged. If till the maximum step size, the algorithm does not converge, then we output the not converged result. And this routine is exact on the tree graphs. When there's no loop on the graph, the converged result is exact. And there's another generalized approximation message passing. This is more general to many different channels. The input is represented by the prior part. Output is represented by the conditioned probability. With any channel, if you can write in this probability distribution form, we can make this algorithm work. And the approximated part is, instead of using the direct message, we use the average and variance of the message as a new messages. And by doing that, the message can be approximately expressed by Gaussian approximation. So all the updates will just matrix multiplication. The complexity is dramatically reduced by this approximation. I will briefly introduce two paper example. This paper is written by me and Yoshiyuki Kabashima and Lenka Bethe-Peierls during my PhD time. We applied replica method and also message passing algorithm on the one-bit compressed sensing. One-bit compressed sensing is a problem in signal processing when we received a signal Y and we know the measurement matrix and we want to predict what's the original signal. And the received Y is only the sign of the output channel. This is the one bit meaning. So another example is paper together with Ayaka Sakata-san. We applied message passing algorithm on the linear regression problem with non-convex regularization scat. This scat is combined L0, L1, and L2 regularization in 3 different regions. And it has 2 controlling parameters, lambda and A. We analyzed this problem by replica method and also made the message passing algorithm. We found that in the parameter space A and lambda space, there's a phase transition between replica-symmetric and replica-symmetric breaking, depending also on other alpha, parameter alpha. So the algorithm is easily converged in the replica-symmetric region and do not converge in the replica-symmetric breaking region. This is known before, but we proved this again with this scat problem. And the time dynamics often calculated by density evolution. This is a graph cited by from Ayaka and Tomoyuki's paper. They did the density evolution on scat problem. 2 micro parameters updating each steps, and the stars is the converged point, is the fixed point of the message passing algorithm. This point is corresponding to the replica symmetric solution. So also here is 2 books in this field, Information, Physics and Computation by Mezard and Montanari. Some of the pictures of this presentation also cited from this book. Another book is Spin Glass Theory and Beyond. And this book is a memorial of the Professor Miguel Villasoro, who has passed away recently. So this is all my talk. Did I talk too fast? I want to welcome questions so I can talk in more details.
Okay, thank you very much for a very clear presentation. So if you have any questions, please go ahead and ask or raise your hand. Okay, Don?
Thank you for the talk. I'm sorry if I missed this. Can you give an example of what a message is?
Message is a distribution.
So it's a real valued function, or
Yes.
I guess also possibly just plus or minus. Okay, so it can be a function, it can be a single value. There are very few limits on what can be passed between these nodes.
It's information passing. So it's condition probability. This remove backslash remove A means when I don't have information from this function node, and only receiving information from other parts, what do I know? What amount of information do I know? And I pass this information to this function node A. Then does A do the same thing to the next neighbor? When I only know this part of graph, what can I know? Then I give this information to this node J. So reiterating this process again and again until converge. Converge means the updates do not move anymore. So the information passing stops.
Yeah,
There's
I
no
guess my question was more, you talk about passing information, and sometimes that information is like a plus or a minus value.
Yeah, it can be plus or minus.
Has like a mean, a variance, like it's a continuous distribution. So I wondered what conceptual limits there are on like what kind of information gets passed.
Messages are normalized. This mark means I didn't write the normalization part, but it's when you only have a binary, but it's 0 or 1 information, then it will be 0.5 passing, because that's the probability of half. So it's always a real number, not a 0 or 1.
Okay.
Real number between 0 or 1.
Thanks.
Okay, any other questions? Okay, Hatsuda-san.
So can you give us some concrete example? I mean, in any kind of message passing in the daily life application of this kind of approach?
Daily life.
So
yeah, so something you familiar to us, like
yeah,
models.
Right.
Coding. It's used a lot.
For example, in which area, or what kind of program?
Signal processing, like cell phones, channel process. We send some signal.
Okay.
Coding theory is we have information, but the codes means you transform it to another message and you send pass to another person. But during the channel, there are noises. The noise it will be represented by conditioned probability in the model, and the received person will have to infer what's the original message information you have sent. The coding theory is you can help to check the error in the channel, even there's noise in the channel, but because of the conditions we intentionally put into the code, then when we receive a code, we use those conditions, we can check, we can improve the inference probability, the ability of the channel.
So does it help also to improve the network so that the probability becomes high or something? Or the network itself is given, and then you try to infer.
Yes, network is given. Yes.
And then in the first part of your talk, you somehow sort of the approximation on the net. Is it the approximation for the network, or is it the approximation for calculating this P? You factorize something. I don't know. It's maybe the first or second pages.
Part?
Yeah. No, it'd be even before. Yes. So you restrict yourself to only to the factor graph, or?
There are many situations. The classical situation is the graph is given. The function is the situation you have. You write it in a function form, but you can also treat the problem in the other way, that you want to infer what's the graph. you have some information of the nodes, then you want to infer what's the edges on the graph. Also, you can do it from the other way.
Oh, okay, I see.
So,
right. Thank you.
Any other question? May I ask then about the point you introduced the Ising models? Maybe it's just the explanation, but in this framework, what can you do with the Ising models?
Message passing algorithm can apply to this model.
And that's also make the Ising model simulation.
Yes,
by messing,
we can do samples also from this distribution. Also infer what's that information on the graph.
Mm-hmm. So if it's ordinary, I guess the Ising model simulations are done by Metropolis method, just distributing those spins randomly and just give some fluctuations. So by using the this message passing, is there any difference or some efficient or target is different?
Compared to what message?
To ordinary.
Ordinary
Ising model method. Usually we just evaluate the Boltzmann weight with random spin configurations, and there is some fluctuation there. So we have some snapshot of the those spin configurations always, and there's a technique to read out the those physical quantities and estimate some scaling law. And I was wondering if this message passing framework is focused on the aspect of
it's
those.
Just another approach. It can do the same thing from compared to other approaches. For example, replica method also is comparable, but it's just different approaches, and it's computationally efficient. Also, you can see the dynamics of the process.
Okay, thank you. Now Iritani-san is raising hand, so Iritani-san.
Yeah, thanks for the great talk, and I'm curious about if this factor graph algorithm work to assess gene to study gene regulatory network in biology or not?
Of course, yes, but the problem is the convergence, because as I talk about stat problem, when it's in the replica-symmetric breaking phase, the standard algorithm will not converge very easily. We need to do some research on that problem. Also, yeah, for real data, it's still not very applicable.
Okay, so in this figure, you assumed some random matrix of the interaction.
From what?
So yeah, I wonder.
In this, it's a model. The measuring matrix is a Gaussian IID distributed matrix. Then we want to infer the hidden signal X vector. We measure it, receive the signal Y, and then the inference problem is done by minimizing this cost function. And the regularization term is a non-convex regularization. And the A here is ideal matrix, Gaussian IID matrix. So if we put like very noisy real data matrix here, then it's it's a problem.
I see. And so I'm also curious about, as Hatsuda-san asked, I'm wondering if this algorithm can, determine the network structure itself or not. Because in many situations, what we want to know is the structure of the network itself. So it is not sometimes given.
Yes, yes, you can also use that way. When you have the spin configuration, then you infer the J, infer the correlations. Also possible to use it in that way.
Okay. So, yeah, okay.
But then you need to change the written form a little bit. It's not very much examined. The algorithm was very focused on this inference of the orange eggs problem in the last 5-10 years. A lot of papers was on this kind of problem. But inferring the A matrix, some research about dictionary learning may be related to that.
Okay. Okay, interesting. Thanks a lot.
All right. Any other questions? Okay, if not, let's thank Yingying again. Thank you very much.